Hello everyone, I'm Soheila, Research Associate at the University of Cambridge, and I'm presenting the Hydroflex project. First, let me start with the motivation. Dams are long-lived and safety-critical structures, therefore operators need reliable as-is information. This supports inspection and risk assessment throughout the service life, not just as design drawings. Next, a digital twin is more than a 3D model. Because geometry alone can't describe how components relate to each other, a digital twin must combine geometry, semantics, and relationships. As a result, it can support automation and advanced analytics. However, standard BIM and IFC schemas were designed for buildings. Therefore, they don't include dam-specific components such as spillways, turbine wells, and intake structures. So instead of forcing dam data into an unsuitable schema, we infer a digital twin-ready model directly from the point cloud. This is the overall pipeline. It is divided into 3 layers. First, we have the geometry processing layer. We process the raw point cloud to remove noise and outliers. Then we segment the point cloud and group the points into individual object clusters. Next, we move to the semantic extraction layer. Here, the object extractor identifies individual object instances. Then the relationship module determines how these objects are connected. Finally, we have the knowledge modeling layer, and the graph builder creates a relationship graph from the extracted information. After that, the UML generator converts the graph into a UML class diagram. This model can then support downstream applications such as BIM integration and analytics. In the next few slides, I'll explain each of these layers in more detail. This is our test bed, the Platonorissi Dam and Hydropower plant in Greece. It is one of the Hydroflex demo sites. The scan covers both the dam structure and the hydropower plant interior. Overall, the dataset contains around 369 million points. This is a very large point cloud. Therefore, scalability becomes a key challenge. Because of this, we design efficient segmentation and mesh generation methods. Simple per-point approaches are not practical for a dataset of this size. Next, this slide shows our labeled interior components. We manually label the turbine hull equipment, pipework, and structural elements. Then we used these labels as the ground truths. After that, we trained and validated the segmentation network. This annotation process was careful and time-consuming. As a result, it allowed us to evaluate the model quantitatively in the next slides. Now let's look at the core segmentation method. The goal is to label every point in the point cloud. In other words, we classify points into objects such as walls, gates, and turbines. So the point cloud is no longer just an unorganized set of points. Next, why do we use deep learning? Because it learns geometric patterns directly from the data. Also, it works well on complex dam surfaces. In contrast, classical methods like random sample consensus often fail on these irregular shapes. Then we use a modified point net with a T-net alignment module and shared multi-layer perceptrons. In addition, we combine it with point net++. This helps capture both large and small components. For the input, we use only X, Y, Z coordinates and laser intensity. We don't use RGB because the scans don't have reliable color information. Also, we use focal loss and tile-based oversampling. This helps solve the class imbalance problem. Finally, the model predicts one of 10 semantic classes for every point. As a result, it clearly outperforms the random sample consensus baseline. It achieves an F1 score of 0.74 compared with about 0.5 for random sample consensus. Now, let's look at the segmentation results. On the left, we have the ground truth labels, and on the right, we have the predicted labels. As you can see, the model matched the annotations very well in most areas. However, there are a few regions where it makes mistakes. This comparison helps us visually assess the model's performance. Now, let's move on to the relationship graph. Segmentation tells us what each component is. However, it doesn't tell us how the components relate to each other. So this relationship graph fills that gap. It adds semantic information, not just object labels. Next, we define two types of relationships. The first is connected, which means two components are close to each other. The second is has, which means one component is inside another region. Then we detect connected components using a k-dimensional tree radius search. We use a distance threshold of 0.5 meters. After that, we check containment with a special region test. This tells us whether a component is inside the dam, the ground, or the turbine floor. Finally, we export the results to a PUML file. Then we use plant UML to generate a draft UML class diagram automatically. So the final output is a relationship graph and a draft UML diagram. This gives the modeler a strong starting point instead of building everything from scratch. This is the hierarchical relationship model. Here you can see the has containment relationships. At the same time, you can also see the connected adjacency relationships. Together, they describe how the dam components are organized. Also, this hierarchy follows the real physical structure of the dam. Therefore, an expert can quickly check whether the relationships are correct. Next, we move from points to a usable surface model. A mesh represents the surface using vertices, edges, and faces. Usually these faces are triangles or quadrilaterals. Therefore, the mesh creates a continuous surface instead of separate points. But why do we convert the point cloud? Point clouds are unstructured, dense, and difficult to process. In contrast, mesh are structured and much lighter. Also, most simulation and visualization tools require mesh. For reconstruction, we use the ball pivoting algorithm, and we use the surface normals from the segmentation step to guide the process. Then we smooth the mesh. Next, we fill small holes. And after that, we simplify the mesh using decimation. However, there are still some challenges. We need to process a very large data set. We also need to fill gaps where the scanner couldn't capture data. At the same time, we must preserve important structural details. Finally, we obtain a clean and structured mesh. As a result, it is ready for analysis, visualization, and beam integration. Here is the mesh output. As you can see, it transforms the raw point cloud into a clean and structured surface. At the same time, it keeps a high level of geometric detail. This is achieved despite the smoothing and hole filling steps. It is important to discuss the current limitations. First, there are a very few open source datasets, so benchmarking and transfer learning are limited. Second, the upstream phase is difficult to scan. It is often underwater or inaccessible. As a result, some geometry is missing. Third, class imbalance is still a challenge. Some classes like cranes, turbine wells, and water tanks each make up less than 1% of the data. Therefore, they are harder to segment accurately. Also, we don't have a ground truth relationship graph yet, and so we can't evaluate graph quality quantitatively. Finally, generalization is another challenge. Different dams have very different designs. Therefore, one pipeline may not work equally well for every site. So, where do we go next? First, we will test the method on multiple dam sites. This will help us evaluate how well it transfers to different dam types. We will also test different materials and scanning conditions. In addition, we will use domain adaptation. This will reduce the gap between synthetic and real scans. It will also reduce the differences between sites. As a result, the method should become more adaptable and robust. Next, we will build a reference relationship graph. This graph will be annotated by experts. Then we can measure edge level precision and recall. We will also test different adjacency distance threshold, including 0.5 meters. This will show how robust the relationship graph is. And finally, these improvements should handle class imbalance better. They should also provide richer semantic information, and overall this will move us closer to scalable digital twins for many hydropower dams, not just one site. Thank you.